Hello, welcome back. Get comfortable. Tonight we're staying close to home. Well, relatively close. We're exploring our solar system, the sun, the planets, the moons, the asteroids, the comets, our cosmic neighborhood. The small corner of space where everything we've ever known has happened, 100 facts. But we have time. 2.5 hours. There's no rush. Each fact is a small story, a detail about worlds you've heard of your entire life, but maybe never really knew. You probably learned about the solar system in school. 9 planets, or 8 now, sorry Pluto, the sun at the center. Maybe you made a model with painted styrofoam balls, but there's so much more to know. Strange details, beautiful quirks, things that make you realize our solar system is weirder and more wonderful than any childhood model could capture. Some facts tonight will be about scale, how impossibly large things are, even in our relatively tiny corner of the galaxy. Others will be about specifics, the color of a sunset on Mars, the sound of wind on Titan, the temperature at the core of the sun. All of it is about home, our extended home, the system that made us, that shelters us, that we're only beginning to explore. If you fall asleep before we finish, that's perfect. Your unconscious mind will keep processing. Maybe you'll dream of planets. Maybe you'll wake up tomorrow knowing something new about Jupiter or Saturn or the asteroid belt. And you won't quite remember where you learned it. That's okay. Knowledge doesn't always need to be consciously grasped. Sometimes it just settles in, becomes part of you. So, let's begin our tour, starting at the center, starting with the sun, the thing that makes everything else possible. The sun contains 99.86% of all the mass in our solar system. Think about that. Jupiter, Saturn, all the other planets, all the moons, all the asteroids, all the comets, all the dust, everything combined makes up less than 0.4% of the solar system's total mass. The sun is 333,000 times more massive than Earth. You could fit 1.3 million. Earth's inside the sun's volume. It's not a planet. It's not like the other objects in our system. It's in a category of its own. Dominant, central, the gravitational anchor that holds everything else in place. This surprises people. The sun isn't burning. There's no combustion happening. The sun glows because of nuclear fusion. In its core, hydrogen atoms are being crushed together under immense pressure and temperature, fusing into helium. This process releases energy, enormous amounts of it. Every second, the sun converts about 600 million tons of hydrogen into helium. The mass difference, about 4 million tons per second, is converted directly into energy, according to Einstein's equation, EMC2. That energy takes about 100,000 years to travel from the core to the surface. Then it takes 8 minutes and 20 seconds to reach Earth. The sunlight touching your face right now began its journey from the sun's core before humans discovered agriculture. The sun's core temperature is about 15 million degrees Celsius. That's where fusion happens. The surface, the photosphere, the part we see, is much cooler, only about 5,500 degrees Celsius. Still hot enough to vaporize any known material instantly, but cool compared to the core. But here's something strange. The sun's outer atmosphere, the corona, is much hotter than its surface. The corona reaches temperatures of 1 to 3 million degrees Celsius. We don't fully understand why. It's called the coronal heating problem. Something is pumping energy into the corona, maybe magnetic field interactions, but we're still figuring out the details. The universe is full of mysteries. Even at the center of our own solar system, a photon, a particle of light, created in the sun's core, doesn't travel straight out. It bounces around, scattered by atoms, absorbed and re-emitted countless times. This random walk can take 100,000 to 200,000 years. The photon zigzags through the sun's interior, gradually working its way outward. Once it reaches the surface, though, it's free. It shoots into space at the speed of light. 8 minutes later, it might hit Earth, enter your eye, get absorbed by your retina, become part of a signal your brain interprets as brightness. That photon started its journey before modern humans existed, and it ended its journey in your eye this afternoon while you were going about your day. The sun isn't solid. It's made of plasma, ionized gas, and because it's not solid, Different parts rotate at different speeds. The equator rotates faster than the poles. At the equator, one rotation takes about 25 Earth days. Near the poles, it takes about 35 days. This differential rotation creates complicated magnetic fields. Those fields tangle, snap, and reconnect, releasing energy in solar flares and coronal mass ejections. The sun is turbulent, dynamic, constantly churning. It's not the steady, unchanging disk it appears to be from Earth. Sometimes the sun releases massive bursts of plasma and magnetic field into space. These are called coronal mass ejections, or CMEs. A large CME can contain billions of tons of matter and travel at speeds up to 3,000 kilometers per second. When one hits Earth, and they do occasionally, it compresses our magnetic field and can create beautiful auroras, but they can also disrupt satellites, damage power grids, and pose radiation risks to astronauts. In 1859, the largest recorded solar storm, the Carrington event, hit Earth. Auroras were visible as far south as Cuba. Telegraph systems worldwide failed. Some operators received electric shocks. Some telegraph papers caught fire. If a storm that large hit us today, with our dependence on electronics, it would cause trillions of dollars in damage. We monitor the sun constantly now, looking for signs of major storms. We usually get about 12 to 48 hours of warning, enough time to prepare satellites, maybe shut down vulnerable power grids, but we can't prevent them. We can only watch and try to minimize the damage. Fact 7. The sun is middle-aged. The sun is about 4.6 billion years old. We know this from radioactive dating of the oldest meteorites, which formed at the same time as the solar system. It has enough hydrogen fuel to continue fusion for another 5 billion years. So it's roughly middle-aged, halfway through its main sequence life. When the hydrogen in the core runs out, things will change. The core will contract and heat up. The outer layers will expand dramatically. The sun will become a red giant, growing large enough to potentially engulf Mercury and Venus. Earth might survive, but barely. It'll be stripped of its atmosphere and oceans. Life will be impossible, but that's 5 billion years away. We have time. Plenty of time to leave if we're smart enough to figure out how. The sun is constantly losing mass. Not just the 4 million tons per second from fusion, but also through the solar wind, a stream of charged particles flowing outward into space. The solar wind carries away about 1.5 million tons of the sun's mass every second. That sounds like a lot, but the sun is so massive that it's losing only about 0.01% of its mass per year. At this rate, the sun will lose less than 0.1% of its total mass over its entire main sequence lifetime. Still, that mass has to go somewhere. It flows outward, filling the solar system, creating a bubble called the heliosphere that extends past the orbit of Pluto. We're inside the sun's atmosphere, in a way, bathed in its wind, protected by its magnetic field. The solar wind eventually meets the interstellar medium, the gas and dust between star systems. The boundary where they meet is called the heliopause. It's about 120 astronomical units from the sun, roughly 120 times the distance. From Earth to the sun, Voyager 1 crossed the heliopause in 2012. Voyager 2 in 2018. They're the only human-made objects to reach interstellar space. Beyond the heliopause, the sun's influence fades. The magnetic field weakens. Cosmic rays from distant supernovae become more intense. It's the edge of our solar system, the boundary between home and the vast galactic wilderness. Sunspots are dark patches on the sun's surface. They appear dark because they're cooler than the surrounding areas, not cool in absolute terms. They're still about 3,800 degrees Celsius. But that's 1,500 degrees cooler than the surrounding photosphere, so they appear dark by contrast. Sunspots are caused by magnetic field activity. Strong magnetic fields inhibit convection, preventing hot plasma from rising to the surface. The result is a cooler, darker region. The number of sunspots varies on an 11-year cycle. Solar maximum, when sunspots are most numerous, corresponds with increased solar activity overall. More flares, more CMEs. We are currently approaching the peak of solar cycle 25, the sun is becoming more active. The sun's gravity is what keeps the solar system together. Every planet, every moon, every asteroid is held in orbit by the sun's immense gravitational pull. At the sun's surface, gravity is about 28 times stronger than Earth's. If you weigh 150 pounds on Earth, you'd weigh 4,200 pounds on the sun. Not that you could stand on it. It's made of gas, and you'd vaporize instantly. But the principle holds. The sun's gravity dominates the solar system. That gravity extends outward, weakening with distance according to the inverse square law. At Earth's orbit, the sun's gravity is just strong enough to keep us moving at 30 kilometers per second, circling the sun once per year. At Neptune's orbit, 30 times farther out, the sun's gravity is 900 times weaker, but it's still enough to hold Neptune in orbit, taking 165 Earth years to complete one revolution. The fusion reactions in the sun's core produce not just energy, but also neutrinos, tiny, nearly massless particles that barely interact with matter. Trillions of neutrinos pass through your body every second, coming from the sun, passing through Earth as if it weren't there. Neutrinos are so difficult to detect that we need massive underground detectors filled with thousands of tons of water or other material, watching for the incredibly rare interaction when a neutrino hits an atom. But we've detected them. Solar neutrinos arriving from the sun's core, confirming that fusion is indeed happening there. They're direct messengers from the sun's interior. Unlike photons, which take 100,000 years to escape the sun, neutrinos travel at nearly the speed of light and escape instantly. The neutrinos arriving at Earth right now left the sun's core about 8 minutes ago. The sun has a complicated magnetic field, generated by the motion of charged plasma in its interior. Every 11 years, the sun's magnetic field flips. The north magnetic pole becomes the south and vice versa. This flip is associated with the solar cycle, the periodic variation in solar activity. We don't fully understand why this happens. It's connected to the differential rotation of the sun's interior and the complex dynamo processes that generate the magnetic field. The sun's magnetic field extends far into space, carried by the solar wind. It creates the interplanetary magnetic field, which fills the solar system and influences the motion of charged particles everywhere. The sun rings like a bell. Sort of. Pressure waves, essentially sound waves, travel through the sun's interior, creating oscillations on its surface. By studying these oscillations, scientists can learn about the sun's internal structure. This field is called helioseismology. It's like using earthquakes to study Earth's interior, but for the sun. The sun has millions of different oscillation modes, each with a different frequency. Most have periods of about 5 minutes. The surface rises and falls by small amounts, invisible to the naked eye, but detectable with sensitive instruments. These oscillations confirm that the sun's core is indeed hot enough for a fusion and provided detailed information about the sun's internal rotation and composition. Why is the sun yellow? Actually, it isn't, not really. The sun's surface temperature of 5,500 degrees Celsius means it emits most strongly in green light. But it also emits across the entire visible spectrum. When you combine all those wavelengths, you get white. The sun is white. It appears yellow from Earth's surface because our atmosphere scatters blue light more than red light. The same reason the sky is blue. When we look at the sun, don't look directly, but hypothetically, we're seeing white light with some blue scattered away. What remains appears yellowish. In space, the sun looks white. Astronauts and satellites see its true color. Earth is the only planet in our solar system where perfect total solar eclipses happen. This is because of a cosmic coincidence. The sun is about 400 times larger than the moon, but it's also about 400 times farther away, so they appear almost exactly the same size in our sky. When the moon passes directly between Earth and the sun, it can completely cover the sun's disk, creating a total solar eclipse. This won't last forever. The moon is gradually moving away from Earth, about 3.8 centimeters per year. In about 600 million years, the moon will appear too small to completely cover the sun. Total solar eclipses will become impossible. We're living in the brief epoch when perfect total eclipses happen. We're lucky. The Sun formed 4.6 billion years ago from a collapsing cloud of gas and dust in our region of the Milky Way galaxy. As the cloud collapsed under its own gravity, the center heated up. When the temperature and pressure reached critical levels, nuclear fusion ignited. The Sun turned on. The remaining material in the spinning disk around the young Sun gradually coalesced into planets, moons, asteroids, and comets. The entire solar system formed within a few 100 million years, so the Sun is older than everything else in the solar system. It was here first. It created the environment where planets could form. It's not just the center of our solar system, it's the reason our solar system exists at all. Sometimes loops of plasma arc off the Sun's surface, following magnetic field lines. These are called solar prominences. They can extend hundreds of thousands of kilometers into space. Some last for days or weeks, suspended above the Sun's surface by magnetic forces. When you see images of the Sun with bright loops of fire arcing off its edge, those are prominences. They're beautiful and massive. Each one could contain several Earths. Sometimes prominences become unstable and erupt, releasing material into space as part of a coronal mass ejection. The Sun is constantly active, constantly changing, never the same from one day to the next. In about 5 billion years, the Sun will run out of hydrogen in its core. Fusion will stop. The core will contract under gravity, heating up in the process. This heat will ignite a shell of hydrogen surrounding the core. The energy from shell burning will push the Sun's outer layers outward. The Sun will expand into a red giant, perhaps 100 times its current diameter. For a brief time, maybe a billion years, the Sun will fuse helium in its core, creating carbon and oxygen. Eventually, even the helium will run out. The Sun isn't massive enough to fuse heavier elements. It will shed its outer layers in beautiful puffs of gas called planetary nebulae. What remains will be the core, a white dwarf, a dense hot ember, slowly cooling over trillions of years. But that's so far in the future, it's almost abstract. For now, the Sun is stable, reliable, providing the energy that makes life on Earth possible. In a sense, Earth orbits inside the Sun's outer atmosphere. The Sun's corona extends far into space. The solar wind flowing from the corona fills the entire solar system. We're bathed in it constantly. Earth's magnetic field protects us from the worst effects of the solar wind, deflecting charged particles around the planet. But we're still technically inside the Sun's extended atmosphere, the heliosphere. 20 facts about the Sun. The star that makes everything possible. The gravitational anchor. The energy source. The reason we're here. Now let's move outward to the rocky worlds. The inner planets, starting with the closest to the Sun, Mercury. Mercury is the closest planet to the Sun, and it experiences the most extreme temperature range in the solar system. During the day, Mercury's surface can reach 430 degrees Celsius, hot enough to melt lead. At night, temperatures plummet to minus 180 degrees Celsius. That's a 600-degree swing between day and night. It happens because Mercury has almost no atmosphere to trap heat or distribute it around the planet. Heat radiates away into space quickly once the Sun sets. Also, Mercury's day is very long. One full day-night cycle takes 176 Earth days, so the night is long and cold. The day is long and scorching. Despite the extreme heat during the day, Mercury has water ice. This surprised scientists. How can the closest planet to the Sun have ice? The answer, polar craters. Mercury's axis has almost no tilt. This means some craters near the poles never receive sunlight. They're in permanent shadow, and temperatures there stay below minus 200 degrees Celsius. Radar observations from Earth and data from NASA's MESSENGER. Spacecraft confirmed that these permanently shadowed craters contain water ice, possibly delivered by comet impacts. So Mercury has both the hottest and some of the coldest locations in the inner solar system. Mercury is shrinking. The planet has contracted by about 7 kilometers in radius since it formed 4.6 billion years ago. This happens because Mercury's large iron core is gradually cooling. As it cools, it contracts, and the surface wrinkles and cracks, forming cliff-like scarps that can be hundreds of kilometers long and several kilometers high. It's like a grape turning into a raisin. But on a planetary scale, Mercury is the densest planet in the solar system if you don't count gravitational compression. Its large iron core makes up about 85% of the planet's radius. We're not entirely sure why Mercury has such a large core. Maybe it formed closer to the Sun where heavy elements were more concentrated. Maybe a massive collision early in its history stripped away much of its rocky mantle. Fact 24. Venus's backwards rotation. Venus rotates backward compared to most planets in the solar system. If you could look down on the solar system from above the Sun's north pole, most planets rotate counterclockwise. Venus rotates clockwise. We're not sure why. The most popular theory is that Venus was knocked over by a massive collision early in the solar system's history. Or maybe gravitational interactions with the Sun gradually flipped it over billions of years. Venus also rotates incredibly slowly. One Venus day, one full rotation, takes 243 Earth days. But Venus's year, one orbit around the Sun, is only 225 Earth days. So on Venus, a day is longer than a year. If you stood on Venus's surface and could somehow survive, the Sun would rise in the west, crawl slowly across the sky over the course of many Earth months, and set in the east. Venus's atmosphere is incredibly dense, about 92 times denser than Earth's. Standing on Venus's surface would feel like being 900 meters underwater on Earth. The pressure is immense. The atmosphere is 96% carbon dioxide, with clouds of sulfuric acid. The greenhouse effect is so extreme that surface temperatures reach 465 degrees Celsius, hot enough to melt lead. Venus is actually hotter than Mercury, even though it's farther from the Sun. The thick atmosphere traps heat so efficiently that temperatures stay uniformly hot across the entire planet, day and night, equator and poles. It's a hellish world. Beautiful from a distance, but utterly inhospitable up close. Venus is covered in volcanoes. More than 1,600 major volcanoes have been identified, and there are probably millions of smaller ones. Most are probably extinct, but some might still be active. Recent observations have detected variations in sulfur dioxide levels in the atmosphere, which could indicate ongoing volcanic activity. Venus's surface is relatively young, about 300 to 500 million years old. At some point in Venus's history, the entire surface was resurfaced by massive volcanic activity. The old crust was buried under lava flows. We don't know if this was a gradual process or a catastrophic event. Some scientists suggest Venus undergoes periodic global resurfacing events, where the entire planet's crust melts and reforms. It's a violent, dynamic world hidden beneath those beautiful, swirling clouds, because Venus rotates so slowly and backwards. It has a very unusual relationship between its day and year. A sidereal day, one full rotation relative to the stars, is 243 Earth days. A Venus year, one orbit around the Sun, is 225 Earth days. But a solar day, sunrise to sunrise, is 117 Earth days. This happens because Venus's orbital motion partially compensates for its slow retrograde rotation. From the surface, the Sun appears to move across the sky faster than the planet is actually rotating. Timekeeping on Venus would be weird. Earth orbits at an average distance of 150 million kilometers from the Sun, one astronomical unit by definition. This places Earth squarely in the habitable zone, sometimes called the Goldilocks zone. Not too hot, not too cold, just right for liquid water to exist on the surface. A bit closer, and Earth would be too hot, like Venus. A bit farther, and it would be too cold, like Mars. Of course, being in the habitable zone isn't sufficient for life. Mars is in the habitable zone too, and it's a frozen desert. You need the right distance from the Sun plus many other factors. A protective magnetic field, plate tectonics, the right atmospheric composition. Earth has all of it. We won the cosmic lottery. Earth has a strong magnetic field generated by the motion of molten iron in its outer core. This magnetic field extends thousands of kilometers into space, creating the magnetosphere. The magnetosphere deflects the solar wind. protecting our atmosphere from being stripped away. Without it, Earth might look like Mars. Atmosphere gradually eroded over billions of years. The magnetic field also creates the auroras. When charged particles from the solar wind get trapped in the magnetosphere, they spiral along magnetic field lines toward the poles. When they collide with atoms in the upper atmosphere, they create beautiful curtains of light, aurora borealis in the north, aurora australis in the south. Earth's moon is unusually large compared to its planet. The moon's diameter is about 1/4 of Earth's diameter. Most moons in the solar system are tiny compared to their planets. Mars's moons are captured asteroids only a few kilometers across. Jupiter's and Saturn's moons, while large in absolute terms, are tiny fractions of their planet's sizes. Earth's moon is different, large, close, visible in detail from the surface. This large moon has profound effects on Earth. It stabilizes our axial tilt, preventing wild swings in climate. It creates tides, which may have played a role in the evolution of life. It lights up our nights. We're lucky to have it. About 71% of Earth's surface is covered by water, oceans mostly with some lakes and rivers. This is unusual. Venus has essentially no surface water. It all evaporated early in its history. Mars has water, but it's frozen, locked in polar ice caps and underground. Earth has liquid water on its surface, vast amounts of it. This liquid water, combined with Earth's temperature and atmospheric conditions, makes life possible. Where did Earth's water come from? Probably multiple sources. Some was trapped in the minerals that formed Earth. Some was delivered by comets and asteroids after Earth formed. The oceans are ancient. They've been here for more than 4 billion years, nearly as long as Earth itself. Earth's atmosphere is 78% nitrogen, 21% oxygen, and 1% other gases, including argon, carbon dioxide, and water vapor. The oxygen is the interesting part. Oxygen is reactive. It shouldn't last in the atmosphere. It should react with surface minerals and disappear. But it doesn't, because life constantly replenishes it. Photosynthesis. Plants, algae, and cyanobacteria split water molecules, release oxygen, and create organic compounds. Earth's atmosphere is not in chemical equilibrium. That's a sign of life. If we detected an atmosphere like Earth's around another planet, it would be strong evidence for biology. We breathe an atmosphere created and maintained by living things. We're part of a planetary-scale ecosystem. Earth is the only planet in the solar system with active plate tectonics. The surface is broken into large plates that move, collide, and subduct. This process recycles crust, regulates climate by cycling carbon, and creates mountains, volcanoes, and ocean trenches. Plate tectonics might be essential for life. It creates diverse habitats, regulates atmospheric composition over geological timescales, and prevents Earth from becoming a frozen or overheated wasteland. Venus doesn't have plate tectonics. Its surface is one solid shell. Mars doesn't either. Its interior has cooled too much to drive plate motion. Earth is geologically alive, active, constantly renewing itself. Mars is red because of rust. Iron oxide. Essentially, the planet's surface has oxidized over billions of years. Mars's crust contains a lot of iron. In the presence of oxygen and water, both of which were more abundant on ancient Mars, the iron rusted, creating the red-orange color we see today. Dust storms carry this rusty dust into the atmosphere, giving Mars's sky a butterscotch color. Even the sunsets are different, blue, because of the way dust scatters light. Mars has been rusting for billions of years. The entire planet is an oxidized desert. Mars's atmosphere is about 100 times thinner than Earth's. The surface pressure is less than 1% of Earth's sea level pressure. The atmosphere is mostly carbon dioxide, 95%, with small amounts of nitrogen and argon. It's so thin that liquid water can't exist on the surface. Water either freezes or sublimates directly from ice to vapor. The pressure is too low for a stable liquid phase. Mars probably had a thicker atmosphere billions of years ago. But without a strong magnetic field to protect it, the solar wind gradually stripped the atmosphere away. Mars lost its magnetic field about 4 billion years ago when its core cooled, and solidified. After that, atmospheric erosion accelerated. What remains is a cold, dry world with a whisper-thin atmosphere. The largest volcano in the solar system is on Mars, Olympus Mons. It's a shield volcano, broad and gradually sloped, like Hawaii's volcanoes, but much, much larger. Olympus Mons is 25 kilometers high. That's nearly 3 times the height of Mount Everest. Its base is 600 kilometers across. If you stood at the base, the summit would be beyond the horizon. The volcano's caldera, the depression at the summit, is 80 kilometers wide and 3 kilometers deep. You could fit multiple cities inside it. Olympus Mons probably formed over billions of years. Mars doesn't have plate tectonics, so the same volcanic hotspot kept erupting in the same location, building up layer upon layer of lava. It's probably extinct now, but it stands as a monument to Mars's volcanic past. Mars has the largest canyon system in the solar system. Valles Marineris, it's 4,000 kilometers long, 200 kilometers wide in places, and up to 7 kilometers deep. If it were on Earth, it would stretch from New York to Los Angeles. The Grand Canyon, by comparison, is 450 kilometers long and 1.8 kilometers deep. Valles Marineris is enormous. We're not entirely sure how it formed. It might have been created by tectonic activity billions of years ago, when Mars was geologically active. Or it might be the result of erosion and volcanic activity combined. Some sections show evidence of water flow, suggesting that rivers once carved through parts of the canyon system. Valles Marineris is a scar on Mars's face, a reminder of a more active, dynamic past. Mars has seasons, just like Earth. This happens because Mars's axis is tilted about 25 degrees, similar to Earth's 23.5-degree tilt. However, Mars's seasons are nearly twice as long as Earth's, because Mars takes 687 Earth days to orbit the Sun. Each Martian season lasts about 5 to 6 Earth months. Mars's orbit is also more elliptical than Earth's, which makes the southern hemisphere's seasons more extreme. Southern summer coincides with Mars being closest to the Sun, making it hotter. Southern winter coincides with being farthest from the Sun, making it colder. The northern hemisphere has milder seasons because the timing is reversed. Mars has polar ice caps, visible even through small telescopes from Earth. They grow and shrink with the seasons. The caps are made of 2 kinds of ice, water ice and carbon dioxide ice, also called dry ice. In winter, carbon dioxide from the atmosphere freezes onto the polar caps. In summer, it sublimes back into gas and the caps shrink. The water ice underneath remains year-round. The southern cap sits on high terrain and is smaller. The northern cap is larger and contains about 1.6 million cubic kilometers of water ice. If melted, it would cover the entire Martian surface in water about 35 meters deep. Mars has water. It's just frozen and locked away. Mars has 2 small moons, Phobos and Deimos. They're probably captured asteroids, dark and irregularly shaped. Phobos orbits very close to Mars, only about 6,000 kilometers above the surface. It's so close that it orbits Mars 3 times per Martian day, but Phobos is gradually spiraling inward due to tidal forces. In about 50 million years, it will either crash into Mars or break apart to form a ring system around the planet. Deimos, farther out, is slowly drifting away from Mars and will eventually escape into independent orbit around the Sun. Neither moon will last forever. Mars's moons are temporary features on geological timescales. We've finished the inner planets, 4 rocky worlds, each with its own character. Mercury with its temperature extremes, Venus with its toxic atmosphere, Earth with its life and water, Mars with its ancient history frozen in rust and ice. Now we move outward, beyond the asteroid belt, to the realm of the giants, the outer planets where worlds are made not of rock, but of gas and ice, where moons are as interesting as planets, where storms larger than Earth have raged for centuries. Let's begin with Jupiter, the king of the solar system. Jupiter is the largest planet in our solar system by far. It contains more than twice the mass of all other planets combined. You could fit 1,300 Earths inside Jupiter's volume. Its mass is 318 times Earth's mass. Jupiter is so massive that the center of mass between it and the Sun doesn't actually lie within the Sun. It's just above the Sun's surface. Technically, Jupiter and the Sun orbit a common point between them. If Jupiter had been about 80 times more massive, it would have ignited nuclear fusion and become a star. We'd live in a binary star system, but Jupiter missed that threshold. It's a failed star, though still the dominant planetary body in our neighborhood. Despite its size, Jupiter rotates faster than any other planet in the solar system. One rotation takes only about 10 hours. This rapid rotation creates Jupiter's distinctive banded appearance. The planet is oblate, bulging at the equator and flattened at the poles because of centrifugal forces. The fast rotation also drives Jupiter's powerful atmospheric dynamics. The bands we see are jet streams, alternating zones of rising and falling gas. The interactions between these bands create the turbulent weather features we observe, including the Great Red Spot. Jupiter is a dynamic, churning world. Nothing about it is static. Jupiter's most famous feature is the Great Red Spot, a massive anticyclonic storm in the southern hemisphere. The storm is larger than Earth. You could fit 2 or 3 Earths inside it, depending on how you measure. We've been observing the Great Red Spot for at least 350 years. Astronomers first noted it in the 1600s, though similar features might have been observed earlier. It's been raging for at least 3.5 centuries, possibly much longer. The storm is shrinking, though. When first measured precisely in the late 1800s, it was about 40,000 kilometers across. Now it's about 16,000 kilometers. Still enormous, but noticeably smaller. We're not sure why it's shrinking or whether it will eventually disappear. Jupiter keeps some secrets. Jupiter has the strongest magnetic field of any planet in the solar system, about 20,000 times stronger than Earth's. The magnetic field is generated by metallic hydrogen deep in Jupiter's interior. Under the immense pressure inside Jupiter, hydrogen is compressed into a liquid metallic state that conducts electricity. The planet's rapid rotation drives currents in this metallic hydrogen, creating the powerful magnetic field. Jupiter's magnetosphere extends millions of kilometers into space. If you could see it from Earth, it would appear larger than the full moon in our sky. The magnetosphere traps charged particles, creating intense radiation belts around Jupiter. These belts are so strong they could quickly kill an unprotected human. Even spacecraft need radiation shielding to survive in Jupiter's environment. Jupiter has 95 known moons, though more are discovered regularly as our detection capabilities improve. Most are small, irregular chunks of rock and ice, probably captured asteroids. But 4 of Jupiter's moons are large, planet-sized worlds in their own right. These 4, the Galilean moons, were discovered by Galileo Galilei in 1610 when he pointed his newly improved telescope at Jupiter. Their names are Io, Europa, Ganymede, and Callisto. Each is a unique world. Io is the most volcanically active body in the solar system. Europa has a subsurface ocean beneath its ice shell. Ganymede is the largest moon in the solar system, bigger than Mercury. Callisto is ancient and heavily cratered, geologically dead. These 4 moons are easily visible with binoculars from Earth. You can watch them orbit Jupiter over the course of a few nights, just as Galileo did more than 400 years ago. The innermost of Jupiter's large moons is the most volcanically active body in the solar system. It has over 400 active volcanoes. The volcanism is driven by tidal heating. Jupiter's gravity squeezes Io, and the other Galilean moons pull on it too. These competing gravitational forces stretch and compress Io as it orbits, generating friction and heat inside the moon. This heat melts rock, creating magma that erupts through Io's surface. Some volcanic plumes shoot material hundreds of kilometers into space before falling back down in Io's low gravity. Io's surface is constantly renewed by volcanic activity. It's the youngest surface in the solar system, geologically speaking. If you visited Io, the landscape would be different from one year to the next. The moon is yellow and orange and red, colored by sulfur and sulfur compounds from volcanic eruptions. It looks nothing like any other moon. Europa, the second Galilean moon, is covered in a smooth shell of water ice. The surface is crisscrossed with cracks and ridges, but has very few craters, suggesting the surface is young and geologically active. Beneath the ice lies a global ocean of liquid water. The ocean is kept liquid by tidal heating, the same process that makes Io volcanic. Jupiter's gravity flexes Europa, generating internal heat that prevents the ocean from freezing completely. The ice shell is probably 15 to 25 kilometers thick. The ocean beneath might be 100 kilometers deep. That means Europa's ocean contains more water than all of Earth's oceans combined. Where there's liquid water, there's potential for life. Europa is one of the most promising places in the solar system to search for extraterrestrial life. NASA's Europa Clipper mission, launching soon, will study the moon in detail, searching for signs of habitability and possibly even biosignatures. Ganymede is the largest moon in the solar system. It's even larger than the planet Mercury. With a diameter of 568 kilometers, Ganymede is about 8% larger than Mercury and 2% larger than Saturn's moon Titan. If Ganymede orbited the Sun instead of Jupiter, we'd classify it as a planet. Ganymede is also the only moon in the solar system with its own magnetic field. This suggests it has a liquid iron core, like Earth. The magnetic field creates a small magnetosphere around Ganymede. Embedded within Jupiter's much larger magnetosphere, the moon's surface shows two distinct types of terrain: dark, heavily cratered regions that are very old and lighter, grooved regions that are younger and tectonically active. Ganymede might also have a subsurface ocean, like Europa. Water sandwiched between layers of ice deep underground, possibly in contact with rock. Another potential habitat for life, Callisto, the outermost Galilean moon, is the most heavily cratered object in the solar system. Its surface is ancient, unchanged for billions of years. Unlike Io, Europa, and Ganymede, Callisto doesn't experience enough tidal heating to drive geological activity. It's geologically dead. The surface we see today looks much the same as it did 4 billion years ago. The craters tell a story of the early solar system when impacts were much more common. Callisto's surface is a record of that violent era, preserved because nothing has erased or covered those ancient scars. Despite its dead geology, Callisto might also have a subsurface ocean. Data from NASA's Galileo spacecraft suggested liquid water might exist deep underground, isolated from the surface by thick ice. Callisto is quiet now, but it holds secrets in its depths. Saturn's rings are the most spectacular feature in the solar system. They're visible even through a small telescope, and they're breathtaking. The rings are made of billions of particles of ice and rock, ranging in size from tiny grains to house-sized boulders. Most particles are ice, which is why the rings are so bright and reflective. The rings extend over 280,000 kilometers from Saturn, but are surprisingly thin. Most of the ring system is only about 10 meters thick. If you scaled Saturn down to the size of a basketball, the rings would be thinner than a sheet of paper. We're not entirely sure how old the rings are. They might be ancient, formed when Saturn did 4.6 billion years ago. Or they might be relatively young, perhaps only a few 100 million years old, formed when a moon broke apart due to tidal forces or a collision. Recent data from NASA's Cassini spacecraft suggests the rings are relatively young. They're bright and clean, not darkened by eons of meteorite bombardment and contamination. This suggests they formed recently in geological terms. Saturn's rings aren't uniform. They're divided into distinct sections, separated by gaps. The most prominent gap is the Cassini division, a 4,800-kilometer wide space between the A and B rings. It's visible even from Earth through a good telescope. These gaps are created by gravitational resonances with Saturn's moons. When ring particles orbit at certain distances, they experience regular gravitational tugs from moons that gradually clear them out of those regions. The moon Mimas, for instance, creates the Cassini division. Particles in that gap orbit Saturn twice for every one orbit Mimas completes. This 2-to-1 resonance creates repeated gravitational interactions that eventually eject particles from the gap. Other gaps are maintained by small moons orbiting within the rings themselves. These shepherd moons gravitationally corral ring particles, keeping them confined to specific regions. Saturn's ring system is a complex gravitational dance between billions of particles and dozens of moons. Saturn is the least dense planet in the solar system. Its average density is about 0.687 grams per cubic centimeter. Water has a density of 1 gram per cubic centimeter. Saturn is less dense than water. If you could find an ocean large enough, Saturn would float. This low density occurs because Saturn is made mostly of hydrogen and helium, the lightest elements. There's a small rocky core at the center, but most of Saturn's mass is gas. Saturn is massive, about 95 times Earth's mass. But it's so large, about 9 times Earth's diameter, that all that mass is spread out over an enormous volume, resulting in low average density. Saturn has a bizarre feature at its north pole, a massive hexagonal cloud pattern. The hexagon is about 30,000 kilometers across, larger than Earth. It's been observed for decades by both Voyager spacecraft and later by Cassini. So, it's a stable, long-lasting feature. We're not entirely sure what causes it. It's probably related to atmospheric dynamics and jet streams, but the precise mechanism that creates and maintains a hexagonal shape is still debated. Computer simulations have created hexagonal patterns in rotating fluids under certain conditions, suggesting this might be a natural consequence of Saturn's atmospheric circulation. But it's strange to see such geometric regularity in a chaotic system like a planetary atmosphere. Saturn's hexagon is a reminder that atmospheric dynamics can create unexpected patterns. Titan, Saturn's largest moon, is the only moon in the solar system with a substantial atmosphere. In fact, its atmosphere is thicker than Earth's. The surface pressure on Titan is about 1.5 times Earth's sea level pressure. The atmosphere is mostly nitrogen, about 95%, with methane and trace amounts of other hydrocarbons. Titan is cold. Surface temperatures are about minus 180 degrees Celsius. At those temperatures, water ice is as hard as rock, and methane can exist as a liquid. Titan has weather. Methane rain falls from methane clouds. Rivers carve channels through ice bedrock. Lakes and seas of liquid methane and ethane dot the polar regions. It's eerily similar to Earth in structure, hydrological cycle, and weather patterns. But instead of water, everything runs on methane. It's a hydrocarbon world, a bizarre mirror of our own planet. Titan has lakes and seas of liquid hydrocarbons. Mostly methane and ethane. The largest, Kraken Mare, is bigger than the Caspian Sea on Earth. It's about 400,000 square kilometers, larger than any of the Great Lakes. These lakes are mostly in the polar regions. The equatorial regions are drier, covered in dunes made of organic particles that have settled out of the atmosphere. NASA and ESA's Cassini-Huygens mission provided detailed maps of Titan's surface using radar to pierce through the thick, hazy atmosphere. The images show a world with coastlines, islands, river deltas, and all the features we associate with a world shaped by liquid. Titan is the only other body in the solar system, besides Earth, with stable liquid on its surface. Not water, but liquid nonetheless. Enceladus, a small icy moon of Saturn, has massive geysers at its south pole that shoot water ice and vapor hundreds of kilometers into space. NASA's Cassini spacecraft discovered these plumes in 2005 and flew through them multiple times, analyzing their composition: water, salt, organic molecules, silica particles. The plumes come from a subsurface ocean beneath Enceladus's icy crust. The ocean is in contact with the moon's rocky core, where hydrothermal vents might exist. Similar to those on Earth's ocean floors, these vents could provide energy and nutrients, creating an environment potentially suitable for life. Enceladus became one of the highest priority targets in the search for life in the solar system. And we only discovered its interesting in 2005. The solar system keeps surprising us. Uranus is tilted on its side. Its rotational axis is tilted 98 degrees relative to its orbital plane. Most planets have tilts between 0 and 30 degrees. Earth is tilted 23.5 degrees, which gives us our seasons. Uranus is tilted so far that it essentially rolls along its orbital path. This probably resulted from a massive collision early in the solar system's history. Something big hit Uranus hard enough to knock it over. Because of this extreme tilt, Uranus has the most extreme seasons in the solar system. Each pole experiences 42 years of continuous sunlight, followed by 42 years of continuous darkness. The sun rises and sets once per Uranian year, which is 84 Earth years long. Imagine a 42-year-long day followed by a 42-year-long night. Uranus's seasonal cycle is bizarre. Uranus appears blue-green in color. This is because of methane in its atmosphere. The atmosphere is mostly hydrogen and helium, but about 2 to 3% is methane. Methane absorbs red light and reflects blue and green light, giving Uranus its distinctive color. Uranus is often described as boring or featureless, especially compared to Jupiter and Saturn with their dramatic storms and bands. When Voyager 2 flew by in 1986, it saw a relatively calm, uniform blue-green ball, but recent observations with better instruments have revealed more atmospheric activity than previously thought. Storms, clouds, atmospheric, features that change over time. Uranus isn't boring. It was just observed at the wrong time. During its calm season, Uranus was the first planet discovered in modern times. Using a telescope, William Herschel discovered it in 1781 while conducting a systematic survey of the sky. He initially thought it was a comet, but further observations revealed it was a planet orbiting beyond Saturn. This was a huge discovery. For all of human history, we'd known only 5 planets visible to the naked eye: Mercury, Venus, Mars, Jupiter, and Saturn. The discovery of a 6th planet doubled the known size of the solar system. Herschel wanted to name it Georgium Sidus, George's star, after King George III of England. But the astronomical community eventually settled on Uranus, continuing the tradition of naming planets after Roman gods. Neptune, the 8th planet, has storm systems similar to Jupiter's Great Red Spot, but they're more transient. When Voyager 2 flew by Neptune in 1989, it observed a great dark spot in the southern hemisphere. This was an anticyclonic storm, similar in structure to Jupiter's Great Red Spot, but when the Hubble Space Telescope observed Neptune in 1994, the Great Dark Spot had disappeared. It had lasted only a few years. Neptune's atmosphere is dynamic. New storms form and dissipate regularly. The planet is the windiest in the solar system, with wind speeds exceeding 2,000 kilometers per hour. Neptune generates more heat than it receives from the sun. This internal heat source drives powerful atmospheric circulation, creating the most violent weather in the solar system, despite being the farthest planet from the sun. We've completed our tour of the giant planets. 4 massive worlds: Jupiter the king, Saturn with its rings, Uranus on its side, and distant stormy Neptune. But the outer solar system isn't just planets. It's full of moons, worlds orbiting worlds. Some of these moons are more interesting than many planets. Let's explore some of the most fascinating moons in our solar system. The prevailing theory for the moon's formation is the giant impact hypothesis. About 4.5 billion years ago, a Mars-sized object called Theia collided with the young Earth. The impact was catastrophic, vaporizing Theia and ejecting massive amounts of material from Earth's outer layers into orbit. This debris coalesced over time, forming the Moon. This theory explains several puzzles about the Moon: why it has a composition similar to Earth's mantle, but lacks a large iron core, why it's so large relative to Earth, why Earth-Moon system has such high angular momentum. The Moon is essentially a piece of Earth, torn away and reformed in orbit. The Moon is gradually moving away from Earth at about 3.8 centimeters per year. This happens because of tidal interactions. The Moon's gravity creates tides in Earth's oceans. The friction from these tides slows Earth's rotation very slightly. To conserve angular momentum in the Earth-Moon system, the Moon must move farther away. Billions of years ago, the Moon was much closer. Days were shorter. Tides were higher. The Moon appeared much larger in the sky. In the distant future, The moon will be so far away that total solar eclipses will no longer be possible. The moon will appear too small to completely cover the sun, but that's hundreds of millions of years away. For now, we get to experience perfect total eclipses. The moon is tidally locked to Earth. The same face always points toward Earth. We never see the far side from Earth's surface. This isn't coincidence. Tidal forces from Earth have synchronized the moon's rotation with its orbital period. One moon rotation takes the same time as one orbit around Earth, about 27.3 days. Most large moons in the solar system are tidally locked to their planets. Io, Europa, Ganymede, Callisto around Jupiter, Titan around Saturn. It's a common outcome of tidal evolution. The far side of the moon, sometimes incorrectly called the dark side, gets just as much sunlight as the near side. We just never see it from Earth. The first humans to see it directly were the Apollo 8 astronauts in 1968 when they orbited the moon. The dark patches on the moon visible to the naked eye are called Maria, Latin for seas. Early astronomers thought they were bodies of water. They're actually vast plains of solidified lava. Between 3 and 4 billion years ago, massive asteroid impacts created deep basins in the moon's crust. Lava from the moon's interior welled up and filled these basins, creating the smooth, dark plains we see today. The Maria are mostly on the near side of the moon. The far side has very few. This asymmetry probably relates to the thickness of the lunar crust and the distribution of heat-producing elements in the moon's interior. The largest Mare Imbrium is about 100 kilometers across. It formed from an impact so large it's hard to imagine. The asteroid that created it was probably 250 kilometers in diameter. Mars's larger moon, Phobos, orbits only about 6,000 kilometers above the Martian surface. It's so close that it orbits Mars faster than Mars rotates. If you stood on Mars's equator, you'd see Phobos rise in the west and set in the east twice per Martian day. It would cross the sky in about 4.5 hours. Phobos is gradually spiraling inward due to tidal forces. In about 50 million years, it will get too close and be torn apart by Mars's gravity, creating a temporary ring system around Mars, or it might impact Mars directly. Either way, Phobos is doomed. Miranda, one of Uranus's moons, has the most bizarre and varied terrain of any moon in the solar system. When Voyager 2 imaged Miranda in 1986, scientists were shocked. The small moon has enormous canyons, 12 times deeper than the Grand Canyon. It has regions of rolling, cratered terrain next to regions with weird grooved and ridged patterns called coronae. Miranda looks like it was assembled from mismatched pieces. One theory suggests Miranda was shattered by a massive impact and then reaccreted, with the pieces coming back together in a jumbled arrangement. Another theory involves cryovolcanism and tectonic activity driven by tidal heating. Miranda's interior might have been warmer in the past, allowing geological activity to reshape the surface in strange ways. We got only one brief look at Miranda as Voyager 2 flew past. It remains one of the most mysterious moons. Triton, Neptune's largest moon, orbits backward compared to Neptune's rotation. This retrograde orbit is highly unusual and tells us Triton wasn't formed alongside Neptune. Triton was captured. It was probably a Kuiper Belt object, similar to Pluto, that wandered too close to Neptune and got gravitationally captured billions of years ago. The capture process was violent. It likely disrupted Neptune's original moon system, causing collisions and ejections. Triton's orbit gradually circularized over time through tidal interactions, but it remains retrograde. Triton is geologically active despite being one of the coldest surfaces in the solar system, about minus 235 degrees Celsius. It has geysers that erupt nitrogen gas, creating dark streaks on the icy surface. Because Triton orbits Neptune in a retrograde direction, tidal forces are pulling it closer to Neptune rather than pushing it away. Eventually, in a few billion years, Triton will get too close and be torn apart by Neptune's gravity. The debris will form a spectacular ring system around Neptune, far more extensive than Neptune's current faint rings. Triton is doomed. just like Mars's Phobos. But it has billions of years left. Pluto's largest moon, Charon, is so large relative to Pluto that they're often considered a binary system rather than a planet and moon. Charon is about half Pluto's diameter. The center of mass between them lies in space between them, not inside Pluto. They both orbit this common point. Pluto and Charon are also mutually tidally locked. Not only does Charon always show the same face to Pluto, but Pluto always shows the same face to Charon. They're locked in an eternal stare, never seeing each other's far sides. If you stood on Pluto's Charon-facing hemisphere, Charon would hang motionless in the sky, never rising or setting. If you stood on the opposite hemisphere, you'd never see Charon at all. Hyperion, one of Saturn's moons, rotates chaotically. Its orientation tumbles unpredictably rather than settling into a stable, synchronous rotation. This happens because Hyperion has an irregular shape and orbits relatively close to Saturn's much larger moon Titan. Gravitational interactions with Titan perturb Hyperion's rotation, preventing it from becoming tidally locked. Hyperion is the only known moon in the solar system with chaotic rotation. If you visited Hyperion, you'd have no idea where the sun would rise or set from one day to the next. The rotation is truly unpredictable over long timescales. Hyperion also has a sponge-like appearance, with an unusually low density. It's probably a loose rubble pile held together by weak gravity rather than a solid body. Mimas, one of Saturn's smaller moons, has an enormous crater called Herschel crater. It's about 130 kilometers across, roughly one-third the diameter of Mimas itself. The impact that created this crater almost destroyed Mimas. If the impactor had been slightly larger or hit with slightly more energy, it might have shattered the moon completely. You can see fractures on the opposite side of Mimas from the crater, probably caused by shock waves traveling through the moon's interior from the impact. Mimas looks like the Death Star from Star Wars because of this giant crater. It's a coincidence, but a fun one. Tethys, another of Saturn's moons, has a massive canyon system called Ithaca Chasma that extends about 3/4 of the way around the moon. The canyon is up to 100 kilometers wide and 3 to 5 kilometers deep. It's one of the largest canyon systems relative to body size in the solar system. Ithaca Chasma probably formed when Tethys's interior froze and expanded, cracking the surface. Or it might be related to the same impact that created the large crater Odysseus on the opposite side of Tethys. Tethys is mostly water ice, with a density close to that of liquid water. It's essentially a giant ice ball orbiting Saturn. Iapetus, one of Saturn's outer moons, has a bizarre two-tone appearance. One hemisphere is bright, covered in relatively clean water ice. The other hemisphere is dark, covered in a reddish-brown material. This contrast is so extreme that early astronomers noticed Iapetus was much brighter on one side of its orbit than the other. The dark material, concentrated on the leading hemisphere of the tidally locked moon, probably comes from dust swept up as Iapetus moves through its orbit. The source of this dust might be other moons, particularly the distant retrograde moon Phoebe, which sheds material that slowly spirals inward toward Saturn. Once a thin layer of dark material lands on Iapetus's surface, it absorbs more sunlight than the surrounding ice. This causes localized warming, which sublimates ice from beneath the dark layer, leaving more dark material behind. The process is self-reinforcing, creating the stark contrast we see. Iapetus also has an enormous equatorial ridge, a mountain range, running along most of its equator. It's up to 20 kilometers high and quite narrow. We're not sure how it formed, but it gives Iapetus a distinctive walnut-like appearance. Dione, another Saturnian moon, has strange bright streaks on its surface called wispy terrain. For years, scientists thought these were deposits of bright, fresh ice. But high-resolution images from Cassini revealed they're actually ice cliffs hundreds of meters high. The bright material is exposed fresh ice on the cliff faces. These cliffs are tectonic features, created when Dione's interior cooled and contracted, or perhaps when it was geologically active early in its history. Dione is cold and dead now, but it was once active. Its surface tells stories of a more dynamic past. Only a few moons in the solar system have significant atmospheres. Titan has a thick nitrogen atmosphere, thicker than Earth's. Io has a thin atmosphere of sulfur dioxide created by volcanic outgassing. Triton has an extremely thin atmosphere of nitrogen. Europa and Enceladus might have tenuous atmospheres created by water vapor from their geysers. Most moons lack atmospheres because they're too small. Their gravity isn't strong enough to hold on to gases, and the solar wind and radiation gradually strip away any atmosphere that forms. Titan is the exception, because Saturn's magnetosphere shields it from the solar wind, and Titan is large enough to hold on to its atmosphere through gravity alone. Many moons in the outer solar system probably have liquid water oceans beneath their icy crusts. Europa almost certainly has one. Enceladus definitely has one, as evidenced by its geysers. Ganymede, Callisto, Titan, Dione, Mimas, and possibly others might have subsurface oceans too. These oceans are kept liquid by tidal heating from their parent planets. The gravitational flexing generates internal friction, which produces heat. These subsurface oceans represent some of the most promising places to search for life beyond Earth. They have liquid water, energy sources from tidal heating, and possibly contact with rocky cores where chemical reactions could provide nutrients. We might find life on a moon rather than a planet. Some planetary rings come from moons being torn apart. Saturn's rings might have formed from a moon that got too close and was destroyed by tidal forces. Mars will likely have a ring system in the future. When Phobos breaks apart, Neptune's faint rings might be sustained by material from small moons being eroded by micrometeorite impacts. Moons and rings are closely related. Moons can create rings. Rings can coalesce into moons. The boundary between the two is fluid on geological timescales. Some small moons, called shepherd moons, orbit within or near planetary ring systems and help maintain the ring structure through gravitational interactions. Saturn's F ring, for instance, is shepherded by two small moons, Prometheus and Pandora, orbiting on either side of it. Their gravity corrals ring particles, keeping them confined to a narrow band. Shepherd moons create gaps in rings, maintain sharp ring edges, and generate waves and other structures in the ring material. They're tiny, typically only tens of kilometers across, but they have disproportionate effects on the ring systems they inhabit. Moons form through several different processes. Some, like our moon, formed from giant impacts. Material ejected from a planet coalesces into a moon. Some formed alongside their planets from the same protoplanetary disk. Jupiter's Galilean moons probably formed this way. Some are captured objects. Triton was captured by Neptune. Mars's moons are probably captured asteroids. Many of Jupiter's and Saturn's small outer moons are captured objects. Each formation mechanism leaves distinct signatures in the moon's composition, orbit, and structure. The most important fact about moons is this: they're not just satellites. They're worlds. Titan has lakes and rain and weather. Europa has an ocean that might harbor life. Io has more volcanic activity than any other body in the solar system. Enceladus has geysers erupting from a subsurface ocean. These aren't just rocks orbiting planets. They're complex, dynamic worlds with their own geology, their own weather in some cases, their own potential for life. The moons of our solar system are some of the most interesting places we know, and we're only beginning to explore them. We've covered the major planets and the most interesting moons. But the solar system contains so much more. Smaller bodies, asteroids, comets, dwarf planets, billions of objects large and small orbiting the Sun. Let's explore some of these smaller inhabitants of our cosmic neighborhood. Between Mars and Jupiter lies the asteroid belt, a region containing millions of rocky objects left over from the solar system's formation. These asteroids are remnants of planetesimals that never coalesced into a planet, probably because Jupiter's gravity prevented them from accumulating. The asteroid belt sounds crowded, but it's mostly empty space. The asteroids are spread over an enormous volume. If you flew through the asteroid belt, you'd be unlikely to see even one asteroid with your naked eye. The distances between them are vast. The total mass of all asteroids combined is less than 4% of the Moon's mass. If you gathered every asteroid together, you'd get something smaller than our Moon. Ceres is the largest object in the asteroid belt, about 940 kilometers in diameter. It's classified as a dwarf planet. Ceres is round, pulled into a sphere by its own gravity. It has a thin water ice crust over a possibly liquid subsurface ocean. Salt deposits on its surface suggest briny water has erupted from below relatively recently. NASA's Dawn spacecraft orbited Ceres from 2015 to 2018, revealing a world more complex than expected. Bright spots and craters turned out to be salt deposits. Some craters showed signs of past cryovolcanic activity. Ceres might have more fresh water than Earth, not on the surface, but locked away in a subsurface layer. Vesta, the second largest asteroid, is a protoplanet. It was on its way to becoming a planet 4.5 billion years ago, but never quite made it. Vesta differentiated into layers like a planet, with an iron core, rocky mantle, and thin crust. A massive impact early in its history exposed the interior, allowing us to study materials from different depths. Some meteorites found on Earth, called Hadees meteorites, come from Vesta. We know this because their composition matches Vesta's surface as observed by Dawn spacecraft. Vesta gives us a window into planetary formation. It's a snapshot of an arrested development, a world that was becoming a planet but stopped partway through. Some asteroids have orbits that bring them close to Earth. These are called near-Earth asteroids, or NEAs. Over 30,000 have been cataloged so far, and more are discovered regularly. Most are small, harmless, but some are large enough to cause significant damage if they hit Earth. NASA and other space agencies track NEAs carefully. Any asteroid larger than about 140 meters that could potentially hit Earth in the next century is classified as a potentially hazardous asteroid. So far, we know of no asteroids on a collision course with Earth, but we keep watching. And we're developing technologies to deflect asteroids, if necessary. NASA's DART mission successfully deflected a small asteroid in 2022, proving the concept works. Comets are often described as dirty snowballs. Chunks of ice mixed with rock and dust. They form in the cold outer regions of the solar system, where water and other volatiles can freeze solid. Most comets reside in two reservoirs, the Kuiper belt beyond Neptune and the Oort cloud, a vast spherical shell of icy objects surrounding the entire solar system. When a comet's orbit brings it close to the Sun, solar heating causes the ice to sublimate. Gas and dust stream off the nucleus, creating the coma and tail we associate with comets. The tail always points away from the Sun, pushed by solar wind and radiation pressure. This means as a comet moves away from the Sun after perihelion, it travels tail first. Halley's Comet is the most famous comet, visible from Earth about every 75 to 76 years. It's been observed and recorded for over 2,000 years. Ancient Chinese astronomers documented it. It appears in the Bayeux Tapestry depicting the Norman conquest of England in 1066. Edmund Halley calculated its orbit and predicted its return in 1758. Making it the first comet recognized as periodic. Halley's Comet last appeared in 1986. It will return in 2061. The comet's nucleus is potato-shaped, about 15 kilometers long. When spacecraft visited it in 1986, they found it was darker than coal, covered in a crust of organic material. The Oort cloud is a vast, spherical shell of icy objects surrounding the solar system, extending from about 2,000 AU to maybe 100,000 AU from the Sun. It's so far away that the Sun's gravity barely holds these objects. They're loosely bound, easily perturbed by passing stars or galactic tides. The Oort cloud probably contains trillions of objects, most smaller than a kilometer across. When one is perturbed and falls toward the inner solar system, it becomes a long-period comet. We've never directly observed the Oort cloud. It's too far away, and the objects are too small and dark. But we infer its existence from the comets that originate there. The Oort cloud marks the edge of the Sun's gravitational influence. Beyond it lies interstellar space. The Kuiper belt is a region beyond Neptune extending from about 30 to 50 AU from the Sun. It's similar to the asteroid belt, but much larger and more massive. The Kuiper belt contains thousands of known objects, probably millions more too small to detect. Most are icy, composed of frozen water, methane and ammonia mixed with rock. Pluto is a Kuiper belt object. So is its moon Charon. Eris, Makemake, and Haumea are other large Kuiper belt objects, all classified as dwarf planets. Short-period comets, those with orbits less than 200 years, mostly come from the Kuiper belt. They're Kuiper belt objects whose orbits got perturbed, sending them into the inner solar system. Pluto's most distinctive feature is a heart-shaped region on its surface called Tombaugh Regio, named after Pluto's discoverer, Clyde Tombaugh. The left half of the heart is a vast plain of frozen nitrogen ice called Sputnik Planitia. It's about 1,000 kilometers across, smooth and nearly crater-free, suggesting it's geologically young. Sputnik Planitia probably formed when an impact created a basin that filled with nitrogen ice. The ice is slowly convecting, like a lava lamp, with warmer ice rising and cooler ice sinking. This convection renews the surface, erasing craters. When NASA's New Horizons spacecraft flew by Pluto in 2015, the heart was one of the mission's most surprising and photogenic discoveries. Pluto has 5 known moons. Charon, Styx, Nix, Kerberos, and Hydra Charon is by far the largest, about half Pluto's diameter. The others are small, irregularly shaped, probably captured objects or fragments from the collision that formed Charon. The small moons have chaotic rotations and orbits with complex resonances. They tumble unpredictably as they orbit Pluto and Charon. The entire Pluto system is fascinating. It's more complex and dynamic than anyone expected before New Horizons visited. Eris is a dwarf planet slightly smaller than Pluto but more massive. It orbits far beyond Pluto, taking 558 years to complete one orbit. Eris's discovery in 2005 prompted the debate that led to Pluto's reclassification as a dwarf planet. If Pluto was a planet, then Eris should be too. But rather than adding planets, astronomers decided to create a new category. Eris is named after the Greek goddess of discord, which is appropriate given the controversy its discovery caused. Eris has one known moon, Dysnomia, named after Eris's daughter. The goddess of lawlessness, Haumea, is a dwarf planet in the Kuiper belt with a very unusual shape. It's elongated, shaped like a football or rugby ball. Haumea rotates very rapidly, completing one rotation in less than 4 hours. This rapid rotation, combined with its relatively low mass, causes it to be stretched out into an ellipsoid. Haumea is about 2,000 kilometers long but only 1,000 kilometers wide. It's the most elongated object in the solar system, large enough to be called a dwarf planet. Haumea also has 2 small moons and a ring system. It's one of only 5 objects in the solar system known to have rings, along with the 4 giant planets. Makemake is another dwarf planet in the Kuiper belt, about 2/3 the size of Pluto. Its surface is covered in frozen methane and ethane, giving it a reddish color. Surface temperatures are about minus 240 degrees Celsius, cold enough for methane to freeze solid. Makemake has one known moon, discovered in 2016. The moon, called MK2, is about 160 kilometers in diameter and orbits Makemake every 12 days. Makemake is one of the brightest Kuiper belt objects which helped with its discovery, but it's still far away and difficult to study. We know less about Makemake than about Pluto or Eris. Sedna is a distant object with one of the most elongated orbits known. At perihelion, its closest approach to the Sun, it's about 76 AU away. At aphelion, it's about 940 AU away. One orbit takes about 11,400 years. Sedna is currently near perihelion, which is the only reason we can see it at all. When it moves toward aphelion over the next few thousand years, it will become too faint to detect even with the most powerful telescopes. Sedna's orbit is so distant that the Sun barely affects it. Something must have perturbed Sedna's orbit to place it so far out. Maybe a passing star billions of years ago. Maybe an undiscovered planet in the outer solar system. Sedna is mysterious, orbiting in the dark beyond the Kuiper Belt. Collectively, objects orbiting beyond Neptune are called trans-Neptunian objects, or TNOs. There are thousands of known TNOs, ranging from small rocks to dwarf planets like Pluto and Eris. Most are icy, primitive objects that have changed little since the solar system formed. Studying TNOs gives us insight into the early solar system. They're time capsules preserving conditions from 4.6 billion years ago. Some TNOs have unusual orbits that suggest the presence of an undiscovered planet in the outer solar system. This hypothetical Planet 9, if it exists, would be several times Earth's mass and orbit hundreds of AU from the Sun. The search continues. We've explored asteroids, comets, dwarf planets, and the distant objects orbiting in the dark edges of the solar system. We've traveled from the Sun to the Oort cloud, visiting dozens of worlds along the way. Now, for our final 5 facts, let's come home. Let's think about Earth, about perspective, about what it means to be part of this solar system. In 1990, as Voyager 1 was leaving the solar system, astronomer Carl Sagan convinced NASA to turn its camera back toward Earth one last time. From 6 billion kilometers away, about 40 AU, Earth appeared as a pale blue dot, less than a pixel. A tiny speck in a beam of scattered sunlight. Sagan wrote, "Look again at that dot. That's here, that's home. That's us. Every person you've ever heard of lived on that dot. Every human achievement, every war, every discovery, every love story. All of it happened on that pale blue dot suspended in a sunbeam. From that distance, Earth's significance is humbling. We're tiny, fragile, alone in the vastness. The solar system is vast, and almost all of it is empty space. If you scaled the solar system so the Sun was the size of a basketball, Earth would be a peppercorn about 26 meters away. Jupiter would be a small orange about 135 meters away. Neptune would be about 780 meters away, and the space between would be empty. Vast distances of nothing. The solar system isn't crowded. It's lonely. Objects separated by distances so large we measure them in astronomical units and light minutes. Fact 98. We live inside a star in a sense. We live inside the Sun's outer atmosphere. The solar wind extends throughout the solar system, creating the heliosphere. Earth orbits within this bubble of solar plasma. We are bathed in the Sun's particles constantly. Protected by Earth's magnetic field, yes, but still technically inside the Sun's domain. The Sun doesn't end at its visible surface. It extends far into space, and we're part of it. The Sun and planets formed 4.6 billion years ago from a collapsing cloud of gas and dust. Most of the material fell into the center, becoming the Sun. The rest formed a disk around the young star. Within that disk, dust grains stuck together, forming pebbles, then boulders, then planetesimals, then planets. The entire process took only a few 100 million years, which is quick in cosmic terms. The solar system we see today is middle-aged. The Sun has about 5 billion years left before it becomes a red giant. The planets will likely survive the Sun's death, though they will be changed forever. We're living in the solar system's prime years. It's stable, mature, comfortable. We've sent spacecraft to every planet in the solar system. We've orbited Mercury, Venus, Mars, Jupiter, and Saturn. We've flown by Uranus and Neptune. We've landed on Venus, Mars, Titan, and several asteroids and comets. We've sent probes beyond the heliopause into interstellar space. We've studied moons, asteroids, comets, and dwarf planets up close. In less than a century, we've gone from wondering what the planets looked like to having detailed maps of their surfaces. We've photographed geysers on Enceladus, volcanoes on Io, lakes on Titan, canyons on Mars. We're learning our neighborhood, one spacecraft at a time, one image at a time, and with each discovery, we realize how much more there is to know. 100 facts. We've completed our journey through the solar system, from the Sun's core to the Oort cloud, from Mercury's scorched surface to Pluto's frozen heart. From the familiar moon to the exotic moons of distant gas giants, this is our home. Not just Earth, but all of it. The entire solar system. 8 planets, hundreds of moons, millions of asteroids, trillions of comets, all held together by the sun's gravity. All part of one interconnected system. We're part of it too. Made from the same materials, following the same physical laws. Connected to every planet and moon by the shared history of our solar system's formation. You now know 100 things about our cosmic neighborhood. Small details that paint a larger picture. A picture of a system that's complex, dynamic, and full of wonders we're only beginning to understand. If you're still awake, thank you for taking this journey with me. I hope you learned something. I hope you feel a sense of connection to the worlds we've visited tonight. If you've fallen asleep, I hope your dreams carried you through the solar system, past Jupiter's storms, through Saturn's rings, across the frozen landscapes of distant moons. The solar system is vast and varied. It's been here billions of years before us. It'll be here billions of years after we're gone, but right now, we're here to witness it, to study it, to explore it, to appreciate its beauty and complexity. That's a gift, a privilege, a moment in cosmic time when conscious beings can look outward and understand, at least partially, the system that made them. Sleep well. Dream of planets and moons and the small corner of the galaxy we call home. Thank you for listening. Clear skies,